This is ominous, and it possesses an enormous mass. Moreover, it's compact. That's three compelling indicators right there, pointing to a supermassive black hole. The cosmos can be daunting to contemplate. The perils that exist within the vastness of space can be frightening. While this applies to the entire notion of space exploration, the aspect that has always been both captivating and unsettling is black holes. These titans of energy have been the focus of numerous research initiatives around the globe. Scholars have been endeavoring to comprehend what black holes truly are and what lies within them. But that all shifts now. Neil deGrasse Tyson has just disclosed something monumental. Our black hole is less substantial than the one at the center of the Andromeda Galaxy, our closest major galaxy. So, we may have black hole envy. I believe we do. We finally glimpse what exists inside a black hole, and honestly, all of it might just astonish you. So join us as we embark on this interstellar voyage and answer one of history's most frequently asked questions. What is a black hole? Formed from a colossal explosion, a black hole's mass is concentrated in an extraordinarily small area, creating a gravitational force so intense that nothing, not even light, can escape it. Once something enters, it remains trapped forever. These energetic phenomena come in various scales, ranging from stellar black holes, which can be several times the mass of the Sun, to supermassive ones that reside at the centers of galaxies and can possess millions or even billions of times the mass of our Sun. Researchers have indirectly observed the effects of black holes for decades, and with every data point we uncover, countless secrets come to light. Even though it appears they are so massive and powerful that they cannot possibly have a backstory, they do. Black holes do not simply exist in space. They are created. They require the remnants of massive stars that have depleted their nuclear fuel to come into being. These stars undergo a supernova explosion, a spectacular event marking the end of their life cycles. During a supernova, the outer layers of the star are forcefully ejected into space, while the core experiences a gravitational collapse. Not all collapses are identical. If the core's mass is several times larger than that of our Sun, the force of gravity overcomes all other forces, leading to an inward collapse. This collapse is so extreme that it compresses the mass into an incredibly small volume, forming an object with a gravitational field so intense that nothing can escape its clutches, thus generating a black hole. The size of a black hole is dictated by its mass. Stellar black holes, which are the most commonly recognized type, have a mass range from a few to several tens of times that of our Sun. At the heart of a black hole lies the singularity, a region of infinite density and space-time curvature. According to our current understanding of physics, the laws of nature disintegrate at this point, and our conventional theories cannot adequately explain what occurs within the singularity. To genuinely grasp the nature of singularities, we must think beyond traditional frameworks. In the realm of physics, a singularity refers to a point in spacetime where certain quantities become infinite or undefined. These singularities manifest in various theoretical contexts, such as at the beginning of an expanding universe, commonly referred to as the Big Bang singularity, and within the interiors of black holes. When we investigate the Big Bang singularity, a fundamental challenge emerges. According to the theory, the universe originated from an extremely hot and dense state about 13.8 billion years ago. However, as we rewind time toward this initial state, the equations of general relativity, which govern the behavior of gravity, begin to falter. This breakdown implies that our current understanding of physics cannot fully account for the conditions at the moment of the Big Bang. Resolving this conundrum necessitates a theory that combines general relativity with principles of quantum mechanics. Black holes harbor singularities at their centers. These regions are where the gravitational pull becomes infinitely strong, and spacetime is highly distorted. According to general relativity, matter and energy that plunge into a black hole reach its singularity and become infinitely compressed. This concept transcends our current comprehension of physics. Compounding the issue, the challenge of singularities has propelled scientists to seek a theory of quantum gravity, which aims to unify the principles of general relativity and quantum mechanics. Quantum gravity aspires to provide a framework that accounts for the behavior of spacetime on both cosmic and subatomic scales. A theory like this could potentially yield insights into the nature of singularities and how the universe truly operates. One approach to addressing the singularity dilemma is the theory of loop quantum gravity. This theory proposes that at extremely small scales, spacetime is quantized, meaning it consists of discrete, indivisible units. These fundamental units are often referred to as loops or spin networks. In loop quantum gravity, the concept of quantization is applied to spacetime itself, suggesting that spacetime isn't seen as a continuous and infinitely divisible entity, but rather as a collection of discrete elements. These discrete spacetime units are often envisioned as interconnected loops or networks representing the underlying structure of the universe's fabric. Within the framework of loop quantum gravity, singularities linked with black holes and the Big Bang could potentially be resolved. One of this theory's key insights is that at extremely small scales, the discrete nature of spacetime prevents the emergence of infinite densities and curvatures that give rise to singularities. In classical general relativity, for instance, in the context of black holes, loop quantum gravity suggests that as matter collapses toward the core, the fabric of spacetime becomes increasingly diminutive. This size limitation prevents the matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters a quantum bounce near the core, where it rebounds and starts to expand again. This scenario leads to the formation of a new spacetime region within the black hole, often referred to as a quantum black hole or a bounce region. Stellar black holes are the most commonly observed variety of black holes in the cosmos. They form through gravitational collapse at the conclusion of a massive star's life. Once a massive star depletes its nuclear fuel, the outward pressure generated by nuclear reactions can no longer counterbalance the gravitational force pulling inward. The gravitational force dominates, causing the star to collapse under its own weight. This collapse results in the creation of a stellar black hole. As the star collapses, it becomes extraordinarily compact, concentrating a significant amount of mass into a very small volume. Consequently, stellar black holes typically have a mass ranging from a few to about 20 times that of the Sun. Despite their mass, they possess remarkably small sizes. Their diameter spans only a few kilometers, illustrating just how extremely dense they are. The immense density of a stellar black hole leads to the creation of an event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon marks the point of no return, where the gravitational pull of the black hole becomes so intense that any object or information crossing it is forever ensnared within the black hole. Next, we come across intermediate mass black holes. While the exact mass range for these black holes remains an area that requires further exploration and refinement, they are generally believed to have masses spanning from thousands to tens of thousands of times that of the Sun. These immense entities inhabit the central regions of most galaxies, including our own Milky Way. They exert considerable gravitational influence over their galactic surroundings and significantly affect galactic evolution. The origins of supermassive black holes continue to be a subject of inquiry and are not yet fully understood, but various theories have been proposed to clarify their formation. One notable hypothesis posits that supermassive black holes develop from smaller black holes through a process known as accretion. According to this theory, as matter, such as gas, dust, and stars, accumulates around a black hole, it forms a rotating disk called an accretion disk. The black hole's enormous gravitational attraction pulls material from this disk, causing it to spiral inward and ultimately merge with the black hole. Over extensive timeframes, this ongoing accumulation of matter allows the black hole to expand to a supermassive scale. During the accretion process, vast amounts of gravitational potential energy are released as matter falls into the black hole. This emitted energy powers some of the brightest and most powerful phenomena in the cosmos. Beyond this, there exist charged black holes, representing a fascinating variation characterized by the presence of an electric charge. There are two main types of charged black holes: Reissner-Nordström black holes and Kerr black holes. Each type exhibits distinct characteristics stemming from the interaction between the black hole's charge and other factors, such as rotation. Reissner-Nordström black holes are charged but non-rotating. They are described by the Reissner-Nordström solution within the framework of general relativity. The charge of these black holes affects the behavior of their gravitational field. However, in terms of their overall structure, Reissner-Nordström black holes resemble uncharged black holes. They possess an event horizon, but the size of this horizon for a Reissner-Nordstrom black hole depends on both its mass and electric charge. In contrast, Kerr black holes are both charged and rotating. They are depicted by the Kerr solution in general relativity. The combination of electric charge and rotation introduces unique phenomena associated with these black holes. One of the notable effects is known as frame dragging, which occurs because the rotating black hole twists the surrounding spacetime. Kerr black holes possess both an event horizon and an inner region referred to as the Cauchy horizon, which acts as an inner boundary separating the external region from where the singularity is located. The presence of electric charge within a black hole generates a repulsive electrostatic force alongside the gravitational force. This electrostatic force can influence the dynamics of particles and matter in the vicinity of the black hole. For instance, charged particles may experience repulsion from a black hole's electric charge, altering their trajectories and behaviors. Although charged black holes are theoretically conceivable, they are not widely expected to exist in nature. Most black holes originate from astrophysical processes that yield neutral objects, meaning they lack a net electric charge. If a black hole were to gain an electric charge, it would likely neutralize itself over time by attracting and capturing opposite charges from its environment. We have learned much about black holes, but actually witnessing one could revolutionize our understanding of these entities. With technology progressing rapidly, scientists have finally succeeded in observing and confirming the existence of a black hole. Indeed, two groundbreaking observations have provided us with direct evidence of black holes. The first direct observation of a black hole took place in April 2019, when the Event Horizon Telescope collaboration captured an image of the supermassive black hole at the center of the galaxy M87. This black hole is situated approximately 55 million light-years from Earth. The image, portraying a luminous ring of hot gas surrounding a dark central region, represents the event horizon of the black hole. The observation validated the existence of a supermassive black hole and provided unprecedented visual evidence of its event horizon and surrounding accretion disk. Following this, observations from gravitational wave observatories like LIGO and Virgo have detected ripples in spacetime caused by the collision and merger of black holes. The detection of gravitational waves in 2015 marked a monumental advance in astronomy and offered indirect evidence of black holes. These observations confirm the existence of binary black hole systems, where two black holes orbit each other and ultimately merge, producing powerful gravitational wave signals. While we are still striving to comprehend these black holes, perhaps even becoming ensnared in their enigmas, for now all we know is that black holes are indeed a reality. It is essential for scientists to continue investigating them to deepen our understanding of their properties, behaviors, and implications for our grasp of the universe. Black holes, despite their mysterious and formidable reputation, continue to capture the imagination of both scientists and the public. These cosmic entities, formed from the remnants of massive stars, exemplify the extreme boundaries of our understanding of gravity and the fundamental laws of physics. As we delve deeper into their mysteries, new questions arise, challenging our current theories and pushing the limits of scientific exploration. One persistent puzzle surrounding black holes is the phenomenon of Hawking radiation, proposed by physicist Stephen Hawking in 1974. Hawking radiation suggests that black holes are not entirely black but emit radiation over time. This radiation is theorized to be generated near the event horizon, where quantum effects near the singularity cause particle-antiparticle pairs to separate, with one particle falling into the black hole while the other escapes into space. If validated, this concept could have profound implications for our understanding of how black holes interact with their surroundings and eventually evaporate over unimaginable timescales. Another research avenue examines the role of black holes in shaping the evolution of galaxies. Supermassive black holes, located at the centers of most galaxies, including our Milky Way, are believed to play a crucial role in regulating star formation and the growth of galaxies through processes such as accretion and feedback. Material falling into the black hole releases immense amounts of energy, influencing the surrounding gas and dust, thereby impacting the formation of new stars and the dynamics of galactic structures over cosmic timescales. The investigation of black holes also intersects with fundamental inquiries in theoretical physics, such as the nature of information and the fate of matter that enters a black hole. According to classical general relativity, information about the matter that falls into a black hole is lost forever, as it appears to be annihilated within the singularity. This presents a profound challenge to the principles of quantum mechanics, which assert that information must be conserved. Recent advances in theoretical physics, such as the holographic principle and the firewall paradox, have sought to reconcile these conflicting viewpoints. The holographic principle suggests that the information within a black hole may be encoded on its event horizon in a lower dimensional form, challenging our conventional understanding of how space and information are interconnected. The firewall paradox, conversely, proposes that the event horizon of a black hole may be surrounded by a firewall of high-energy particles, which could resolve the issue of information loss but raises new questions about the nature of spacetime in proximity to the black hole. Beyond theoretical speculation, observational astronomy continues to provide new insights into the behavior and diversity of black holes throughout the cosmos.